Trying to fall into the sun sounds like an easy thing to do. Just let yourself go, right? But the reality is quite the opposite. In the universe, things don't work out the way one would think. In fact, it's much simpler to launch a spacecraft out of the solar system than it is to crash it into our star. How can this be possible? What invisible forces prevent this? Today we will tell you why sending something to the sun is one of the most difficult challenges in space exploration. Let's get started. I've always wanted to read more books on mindset and personal growth, but honestly, I rarely had time to focus or finish them. Shortform changed that for me. Instead of rushing through, I can open one guide and actually understand the lessons. The one-page overviews keep it simple. The chapter breakdowns go deeper, and the exercises help me bring the ideas into real life. When I read The Power of Now, I finally understood how to apply it, because short-form connected Tolle's ideas to modern writers like Ryan Holiday. It felt less like reading theory and more like building habits I could keep. Getting anything into space is extremely difficult. Nowadays, spacecraft launches are becoming increasingly frequent and have become so commonplace that we often forget that sending any object into space is actually extraordinarily difficult. Escaping Earth isn't as simple as building a rocket and aiming it at the sky. It is a feat that requires overcoming a concrete physical barrier, the escape velocity, which on our planet is approximately 11.2 kilometers per second. That is more than 25,000 miles per hour. To give you an idea, that's almost 30 times faster than a rifle bullet. Exceeding that speed requires a monumental amount of energy and, of course, fuel. The Saturn V rocket, which carried the Apollo astronauts to the moon, was more than 360 feet tall and contained more than 2 million liters of fuel, including liquid oxygen and kerosene. And that was just to put a small capsule into lunar orbit. When it came to sending the Parker Solar Probe toward the Sun, the complexity was even greater. Although its tanks were smaller, the Parker required multiple launches, gravitational assists, and painstaking planning, which made its journey take several years. But even if we manage to get a rocket off the Earth, it is still trapped in the Sun's orbit because our planet travels around our star at about 30 kilometers per second or nearly 67,000 miles per hour. This means that any spacecraft we launch inherits that same orbital velocity. To escape the solar system, as the Voyager 1 and Voyager 2 probes did, we simply need to apply an extra boost in the same direction as our orbit, thus increasing speed in order to escape the gravitational pull of the Sun. But to do the opposite, to fall towards the Sun, we must reduce that speed significantly, to the point where the orbit intersects the Sun's surface. And this is what complicates the whole matter. Braking from 30 kilometers per second until you are entirely at the mercy of the Sun's pull implies imprinting a contrary impulse of similar magnitude, which is equivalent to a monumental effort. First, you have to reach a very high speed and then brake suddenly with the bit of fuel available. It would be like accelerating a bullet train to full speed and then trying to stop it without using the brakes, using only a small fan blowing in the same direction the train is moving. It's that difficult. Journey to the Sun. Suppose we have already achieved the unthinkable, reducing the orbital speed of a spacecraft in the direction of the Sun. What's next? The answer may sound simple, but it hides an even greater challenge. Now you have to accelerate to reach the Sun and then brake so as to not pass by. Seems counterintuitive, right? But it is so. Although one would think that the Sun's gravity should absorb and attract any nearby object to it, the truth is that although solar gravity acts like a magnet that pulls you towards its center, all bodies within the solar system that are in orbit around the Sun will continue to be so unless a force forces them to change that movement. In other words, a spacecraft going straight to the Sun needs to slow down at just the right time, or else it will continue to spin in a stable orbit for thousands or even millions of years. The Parker probe, for example, was not launched in a straight line toward the Sun. In reality, its trajectory included a series of exact maneuvers, 7 flybys of Venus over nearly 7 years, completing 24 elliptical orbits to approach our star gradually. This process was not accidental. It served to gradually slow down the initial speed inherited from being in Earth's orbit, which is about 67,000 miles per hour or 30 kilometers per second. Without those maneuvers, the probe would simply have continued to orbit the Sun like a planet. This is one of the most common mistakes when imagining space missions, thinking that aiming for the destination and accelerating is enough. But space doesn't work like that. Every spacecraft launched from Earth already travels at enormous speed around the Sun, and changing that trajectory requires a lot of energy. And this is where the real problem arises: slowing down. At its closest point to the Sun, the Parker probe travels at about 430,000 miles per hour, more than 690 kilometers per hour, and even then it doesn't collide with the Sun. This leads us to a logical question. Wouldn't it be enough to slightly alter its orbit for it to impact the Sun directly? In theory, yes, but even a minor correction that lowers the lowest point of the orbit, perihelion, to the solar surface requires enormous energy expenditure. To better exemplify this, imagine you are caught on the edge of a tornado spinning at tremendous speed. Suppose you want to freefall toward the center. In that case, you must first decelerate enough to escape that force that keeps you spinning, and then plummet towards the center. But unlike a tornado on Earth, in a solar orbit, you don't have the option of using a parachute or something to slow down with friction. The only way is to burn a lot of fuel to brake. And when you're traveling at hundreds of thousands of miles per hour, even a slight reduction means an enormous amount of fuel that no modern spacecraft possesses. So if we don't have a spacecraft that can carry enough fuel to slow down and fall towards the Sun, does that mean that crashing into the Sun is impossible? No, there's actually a way to brake enough to hit the Sun, and it consists of a well-known method, which we have mentioned a lot on this channel. Gravity assist as a braking method. Did you know that gravitational assist can not only be used to accelerate, but also to brake? But how exactly does it work? Imagine a spaceship approaching a moving planet such as Venus. As it approaches, the planet's gravity pulls it in, accelerating it. But if the spacecraft enters at the right angle and exits in the opposite direction to that of the planet's motion, it may lose speed with respect to the Sun, even though it has gained relative speed with respect to the planet itself. In other words, the planet robs the spacecraft of a bit of speed and, in the process, helps it get closer to the Sun. This effect can be used for both acceleration and braking, depending on the angle and trajectory of entry. This method has been used in several missions. A recent example is the Bepi-Colombo probe, launched by the European Space Agency and JAXA to study Mercury. To get to that small planet, which is so close to the Sun and moving so fast, the spacecraft had to perform multiple flybys, 1 over Earth, 2 over Venus, and 6 over Mercury, each designed to progressively slow its speed relative to the Sun and allow it to enter a stable orbit around Mercury. Without these gravitational assists, it simply wouldn't have been possible to reach its destination without consuming ridiculous amounts of fuel. The same goes for the Parker probe, which is using 7 flybys of Venus over the course of its mission to get closer and closer to the Sun. With each pass, its perihelion, the closest point to the Sun in its orbit, shrinks, allowing it to study regions closer to the solar surface without the need for huge propulsive impulses. Gravitational assist is such a powerful tool that even spacecraft traveling to the far reaches of the solar system, such as Voyagers, used it to propel themselves. But in the case of the Sun, the objective is the opposite: to slow down. And for that, the help of planets like Venus is crucial. This type of maneuver requires exact calculations: the angle of entry, the relative velocity, the exact position of the planet. Everything needs to be synced seamlessly. If something goes wrong, the spacecraft can be thrown in an unwanted direction or lose the opportunity to perform the flyby. But when done right, the rewards are enormous. A significant reduction in speed without needing to spend a single drop of extra fuel. Now suppose that a spacecraft like the Parker probe finally manages to reach an orbit close to the Sun. How does it survive there? After all, temperatures near the Sun must be thousands or even millions of degrees, correct? Surviving the Sun's heat. Getting close to the Sun is not only complicated by speeds and trajectories, but also by a much more direct threat: extreme heat. As a spacecraft approaches our star, solar radiation becomes exponentially more intense. To put it in perspective, the Parker probe will come within just 3.8 million miles of the Sun, where the radiation is more than 500 times greater than what we receive on Earth. Any conventional ship would melt in seconds. Fortunately, the Parker probe is not a conventional spacecraft. Its survival is possible thanks to a revolutionary heat shield, the Thermal Protection System, or the TPS. This shield, just 4.5 inches thick, is made of a carbon-carbon composite capable of withstanding temperatures of up to 2,500 degrees Fahrenheit. In addition, it is covered with a white ceramic layer that reflects a good part of the solar radiation, preventing it from reaching the rest of the spacecraft. Behind that shield, the scientific instruments are protected in the shadows, and while the sun-exposed side reaches hellish temperatures, the inner part of the spacecraft maintains an almost terrestrial environment, around 85 degrees Fahrenheit. That temperature difference is one of the most impressive achievements of space engineering. However, heat is not the only problem. The Parker probe also faces an environment charged with solar particles, intense magnetic fields, and highly energetic solar wind. Therefore, all its components are carefully placed within the shield's shadow cone. Even the solar panels which power the spacecraft are designed to partially retract when it approaches the sun, exposing only what is necessary to continue operating without overheating. In addition, the probe features an active cooling system which uses deionized water to absorb and dissipate heat from critical components. It is the most sophisticated cooling system ever incorporated into a spacecraft. And although it may seem that the probe stays next to the sun, this is not the case. Its orbit is elliptical. It enters, approaches briefly, takes data, and moves away. This avoids prolonged exposure and repeats this cycle several times. Each approach brings it closer than the last, allowing scientists to collect data without compromising mission integrity. During these approaches, Parker has even crossed the solar corona, the sun's outer atmosphere, where temperatures exceeded 1 million degrees Fahrenheit. But paradoxically, as the particle density of this region is very low, the heat it transmits by contact is minimal. The real threat is direct radiation. Thanks to this combination of shield, intelligent design, and orbital maneuvers, Parker continues to operate successfully where no other spacecraft has dared to enter. But what will happen once the Parker probe manages to get close enough to the sun? Will it ever hit the sun? Landing on the sun's surface. Reaching the sun's orbit is already an extraordinary achievement. But if the goal were to go further, not just orbit, but to land or instead crash into its surface, then the mission becomes even more challenging. Because once you're in a close orbit, the only thing keeping you from falling into the sun is your own orbital velocity. To achieve the landing, you have to eliminate that speed, and doing so is not easy. The Parker probe, for example, travels at more than 430,000 miles per hour on its closest approaches. That speed is what keeps its orbit stable around the sun. If we wanted to fall directly into the star, we would have to apply an impulse in the opposite direction of its motion that reduces its speed to zero. Only then would it stop orbiting and begin a free fall towards the sun. The problem is that this maneuver requires a gigantic amount of energy, far above what any current ship can provide. Now, someone might ask, what about the flybys of Venus? Couldn't they be used to push this spacecraft into a direct collision orbit with the sun? The answer is that, in theory, yes, but in practice, it's not that simple. As we mentioned earlier with the tornado example, gravitational assists have physical limits. They progressively modify the spacecraft's trajectory to reduce its orbital speed with respect to the sun. It is an efficient method, but not unlimited. You can't just do a flyby and expect to reduce your perihelion from 5 million miles to 0 miles. Each flyby can only reduce perihelion to a certain extent, and getting closer than that would require a final maneuver with active propulsion, which in the case of Parker is not planned. In addition, the closer you are to the sun, the fewer options you have to perform new gravitational assists. Venus is the last helpful planet for this type of maneuver. Mercury's low mass makes it less effective for gravity assists compared to Venus. After that, you're on your own, and if you were to try to force a collision orbit, the precision required would be extreme. Any slight mistake would send the spacecraft on the wrong trajectory or cause it to miss the chance of impact. And that's not to mention the most crucial detail. Even if you managed a collision trajectory, the ship wouldn't survive to tell the story. The Sun does not have a solid surface like Earth. Its atmosphere, made up of the photosphere, chromosphere, and corona, is composed of plasma at temperatures up to 3.6 million degrees Fahrenheit. Any spacecraft that enters there would disintegrate long before reaching the center, even the Parker probe. So in short, landing on the Sun is a theoretically possible but practically unfeasible concept. It requires reducing a brutal orbital velocity, which cannot be achieved with gravitational maneuvers alone. Additionally, it involves facing a thermal and energetic environment that no current human technology can withstand. For all these reasons, crashing into the Sun is much more difficult than simply leaving the solar system. As we can see, the simple fact of orbiting the Sun makes colliding with it almost impossible. The only way to get closer is to orbit it for a long time, like the Parker probe. But if that's the case, what about the planets? They have been orbiting the Sun for billions of years without colliding. Why? Why do all planets, including Earth, still orbit the Sun? If you want to know the answer to that question, watch this video.